On record, and let's start talking about calculus.
Yes, sir.
First of all, there's two kinds. There's differential calculus and there's integral calculus.
All right. Differential and integral.
Yeah, I don't know that you want to be taking notes, to be honest with you.
Yes, sir.
I just don't think, I know that that's what most people do, and boy, they don't like it when I try to mess with it. I don't blame them. If you know how you learn best, then do whatever you want. But I think the best thing is going to be for you to have your attention on my screen.
Yes, sir.
And today it'll be mainly instructional stuff, because I need to give you the premise of calculus before we can start doing problems.
Yes, sir.
And what separates calculus from algebra, geometry, and trig is limits.
Limits.
Limits. You have not had limits yet. You take algebra, geometry, and trig, you combine them with limits, and you've got differential calculus. And the other side of the coin is integral calculus. And the reason I say the other side of the coin is because it is the inverse. It's like if you take x squared and you want to undo that, you take the square root of x. So the square root of x is the inverse of x squared. Multiplication is the inverse of division. Differential calculus is the inverse of integral calculus. Even though when you study each one of them, they don't appear to be that. It's really difficult. In fact, they were developed completely independent of one another.
Really?
Yeah, Sir Isaac Newton developed one of the two. I can't ever remember. And Leibniz from Germany developed the other one. And they both published 20 years apart from one another and didn't realize at the time that one was the inverse of the other. Eventually, they both learned of the other's work, and they came to understand calculus the way we do today. But it was rather surprising at first. There were two different maths, and they happened to be just opposite sides of the same coin.
It's crazy.
So, without calculus, you can handle, I'm going to ignore the first one for a moment. We'll come back to that. It's a little confusing. Without calculus, on the left, you can figure out the slope of a straight line.
That's right.
With calculus, differential calculus, you can figure out the slope of the straight line that is tangent to a curve. On the left, without calculus, you have a secant line to a curve. Crosses that line in 2 points. With calculus, you have the tangent line to the curve. And if you had to sum up differential calculus in 5 words, those would be the 5. The tangent line, actually it's the slope of the tangent line to a curve. Or generally just the slope of the tangent line. And that's what we're going to kind of work on today also.
Okay.
Back on the left, we can figure out an average rate of change or speed. If you drive from Florida to here, you take the total number of miles divided by the total number of hours you took to drive, and that's your rate of speed, your average rate of speed.
Yes, sir.
With calculus, we can figure out the instantaneous rate of change. Because all you have to do is go out in your car and drive and look at your speedometer. That is the instantaneous rate of change.
So it's the same thing as the tangent.
Yes, basically. This tangent line to a curve is measuring the rate of change of that function.
The instantaneous.
Only instantaneous. And we'll see why that's a problem. Notice that the slope of any line is rise over run, correct?
Yes, sir.
Well, the rise is 0 and the run is 0. So when you're looking at the slope of the tangent line to a curve, It's 0 divided by 0. And that's where limits come in.
Okay.
That allow us to figure out what that slope is. Let's just talk about a couple of these other things. Without differential calculus, you can figure out circles, but you can't figure out curves very well. With curves, you need differential calculus, unless it's just regular curves like circles or semicircles. Notice in your geometry class, you never dealt with curves like this over here on the right.
That's right.
What you always dealt with was circles, cylinders, things like that, which we know the geometry of. But
yes, sir.
Figuring out the curvature of that curve, whole new story. That requires calculus.
Yes, sir.
The height of a curve, let's see, the next one. All right, without calculus, we can figure out the height of a point on the x-axis. Okay, the height of that point would be f of c.
F of c.
In other words, here, let me do one thing to their diagram here. What we really want to use is f of x notation for the y-axis. And so when we're referring to that height right there, that height is f of c. Don't worry about putting a number on it. That's a big part of calculus, is understanding this principle right here. That value is f of c.
That's right.
Okay. On the right, using differential calculus, we can figure out exactly where that point occurs. We can figure out that it occurs at that point on the x-axis, and we can figure out what it is. So that's powerful, because there's a lot of things where you need to know where the highest or the maximum is.
Wait, so you can assign its exact value?
Well, you have to do some calculus first, but we're getting to that. What I'm doing right now is just giving you an overview of what the difference between calculus and everything previous to it is.
Yes, sir.
On the left, we can figure out a tangent plane to a sphere. On the right, we can figure out a tangent plane to any kind of a curved surface, sphere or not.
Wow.
On the left, we can figure out the direction of motion along a line. On the right, we can figure out the direction of motion along a curve. Close that out. Open up the integral calculus. This is from that book, incidentally. It's another, you don't particularly have to have a book, is that I can always post images. Hold on. Just a second. For some reason, I have a terrible time moving this thing out of the way when it's here. When it's compressed. Okay, with integral calculus, well, without integral calculus, we can figure out the area of straight-edged objects, like rectangles and triangles.
Okay.
Or the volumes of cubes or rectangular bricks, anything that doesn't have curves in it. We can also handle circles and spheres. But that's about it.
Because we know their geometry.
Well, it's not that. It's that you got to have this concept of limits to be able to deal with curves.
Okay.
Okay. Notice what you can do on the right. You can figure out the area under that curve. In other words, the shaded area in pink. You've never had the ability to do that. This area right here.
Huh.
This area right here. Integral
That's right.
calculus is all about that. In fact, if you had to use 4 words to describe integral calculus, these would be the 4. It is the area under a curve.
Okay, so integral
Integral is where you see that thing a lot. That's an integral sign.
okay.
Okay?
Yes, sir.
Okay. With integral or without integral calculus, you can figure out the work done by a constant force on the left. With integral calculus, you can figure out the work done by a variable force, a force that's constantly changing. It's not constant. With regular geometry, you can find the center of a rectangle. With integral calculus, you can find the centroid of a region.
Centroid. So what's the difference?
The centroid of this region is, well, there's a way to define it, but that's where it's located. And we don't need to get into that yet.
Okay.
As to how you do it. The fact is that we'll have the ability to do it.
Yes, sir.
With straight lines, you can figure out the length of a line segment with geometry. Well, with calculus, you can figure out the length of an arc, a curved line. In other words, if you take this arc over here on the right, and it was a piece of thread, and you wanted to know exactly how long it was, so you'd pull it taut, measure it. Well, we don't have to pull it taut. We can figure out the length of that arc as it stands. With geometry, we can figure out the surface area of a cylinder, but with calculus, we can figure out the surface area of any solid of revolution. Strange shapes.
Really?
We can also figure out the volume of solids of revolution. Let me go down here and see if there's anything else.
Okay.
The mass of a solid of constant density. Over here on the right, we can figure out the mass of a solid of variable density. Again, you can kind of see the difference between the two. Calculus is all about working with curves.
That's right.
Over here, the very last one at the bottom, the sum of a finite term of numbers. You've done that with your series, your arithmetic series and your geometric series.
Yes, sir.
That was pre-calc. Okay? With calculus, you can figure out the sum of an infinite number of terms. For example, what is the sum of this sequence?
That is...
It's an infinite series. In other words, here's how we write it, where n goes from 1 to infinity. So it goes on forever, but it is does not diverge, it converges to a number. The number is 1.
Is that 1 over n squared or 1 over 2n?
Yeah, you're right. It's 1 over 2 to the nth power. Like that.
Yes.
But that's an infinite, a lot of people would find that rather amazing, that you could have an infinite series and
it's a finite answer.
It's a finite answer, because most people would think if you have an infinite series, you have to have an infinite answer. If I take this series up here, that does not converge, that diverges. That goes to infinity.
That's right.
So, okay, let's get back. I think I'm done with these all of these pages. So let me close these out and let's start talking about the normal way someone's introduced to calculus is with limits. You spend maybe 2 weeks on limits.
Limits.
We're going to certainly spend our time on limits, but the one question I invariably get asked by a student is, what is the reason we're studying limits? They'll spend 2 weeks doing these really difficult limit problems, and there's absolutely nothing yet that indicates there's any use of it.
Okay.
Let's talk about the most basic differential calculus, which is figuring out the slope of the tangent line.
Slope of the tangent line.
So I'm going to put a curve on here.
Okay.
That is f of x equals x squared. Your basic quadratic parabola. And
Yes, sir.
if I want to find the slope of that, the tangent line to that point right there,
All right.
instantaneous at that point only, we'll call it x.
X. Okay.
Okay. Well, what's this point right here?
That is going to be
F of x.
f of x.
Even though this is also f of x, not to confuse you, but if we're going to call this point on the x-axis x, then the point on the y-axis is f of x.
That's right.
Okay? Now notice the problem in figuring out the slope of that tangent line. I can draw it, I can kind of estimate how best to draw it, but when I look for the rise over the run, I get 0 over 0. There's no rise, and there's no run. So here's what we do. We find another point out here, which I will label x plus h.
X plus h.
And what's this point going to be?
F of x plus h.
And I will draw a secant line.
Okay.
Can I figure out the slope of that secant line?
You can. Well, if you know the coordinates of f of x, and
so what would it be? It would be the rise is f of x plus h minus f of x, right?
that is right.
And the run is
X plus h minus x.
so you get the slope of that secant line. This distance between x and x plus h is h, right?
Yes, sir.
Label that with h. But that's not the slope of the tangent line at x.
That's right.
So let's start moving it closer. I'm going to move this point here a little bit closer to our point. Yeah, getting closer to what would look like the slope of the tangent line. Let's make h even smaller. Put it right there. Now that secant line is looking better and better. What if we let h go to 0? So that the only thing we see is that. That's going to give you the slope of the tangent line. So,
But does that make a 0 on the denominator?
well, hold on a second. The definition of first derivative is
First.
the limit of this function as h approaches 0. With me? The bottom, the x's cross off, so you end up with just h in the bottom.
Okay.
So you end up coming awfully close to dividing by 0, which breaks the number one commandment in all of mathematics. Thou shalt not divide by 0.
It comes close to.
That's the key. H never reaches 0, it just comes close.
It never reaches 0.
Well, it kind of does. By the time you get it all the way to x, it actually does reach 0. But using limits, I'm going to show you out how to figure out what this limit would be as h goes to 0. In fact, let's just do it real quick. Math, this can be a little complicated, but this curve is x squared. Okay?
Yes, sir. That's right.
Here's what I'm going to do. I'm going to say it's the limit as h goes to 0 of x plus h squared. Is that not f of x plus h?
Yes, sir.
Minus x squared, which is f of x, all divided by h. Now, can we figure out what that limit is? Well, let's look at it further. If I expand that, here's what I get. X squared plus 2xh plus h squared minus x squared all over h. I'm taking the limit of that as h approaches 0. Well, notice what happens. That cancels with that. I can factor an h out from the remaining two terms.
That's right.
Cancel it with the bottom, so this top ends up becoming 2x plus h. And I'm going to take the limit of that as h goes to 0. Well, what's the limit of 2x plus h as h goes to 0?
Would that just be 2x?
That is the first derivative of that function. If I want to write it, I'll write it like this up here in the upper left. And what that means is that no matter where I'm at on the x-axis, let's put us at a number, 5. If I want to know the slope of the tangent line right there, guess what it is?
2x.
It's 2 times 5, 10.
2 times 5.
That's the slope of that tangent line. If I were to draw it, it would be very, very steep. And the instantaneous rate of change of that function at 5 is 2 times x.
Yes, sir.
Okay? So what happened over here on the right was almost magical. We started out with something being divided by 0, and it turned out that we weren't dividing by 0 at all. We ended up with 2x plus h as our answer.
Yeah.
So I'm adding a differential. Incidentally, that's what these are called.
Yes, sir.
Called differentials. And what they basically mean is very, very, very tiny increments that approach 0 but never reach 0, theoretically.
Differential. So you have delta x, is that right?
Well, these are just terms you'll run across when studying differential calculus.
Okay.
They all pretty much mean the same thing. delta x means a very, very small change in x.
All right.
That's what we had up here. Instead of delta x, I used h. And h is what the textbooks usually use on this official derivative definition. And this really, truly is the official derivative definition. And I'm shocked at myself because I did something that I've been criticizing teachers for doing for 10 years, which is starting with the hardest part. It's going to get much easier. I fell into it in explaining how you calculate this slope of the tangent line.
Yes, sir.
What I'm not going to make you do is all of various functions figuring out their derivative using this definition. There's a much easier set of tools to figure out these derivatives.
Okay.
And that's what I object to, is that it's one thing learning this, because this is a fairly new concept that you've never been exposed to before, where you're taking a limit of a function. Okay? Let me add something else. Arithmetic is manipulation of numbers.
That's right.
Algebra is the manipulation of variables that can be numbers.
Okay.
Calculus is the manipulation of functions. Functions like x squared, square root of x, sine x, log x, e to the x. All of those we're going to manipulate using calculus, both differential calculus and integral calculus. Both of them are all about manipulating functions. Okay? Now, I'm going to erase this page and put up another quick page to just give you a quick overview of integral calculus. But I think you can see the differential calculus, this limit concept is huge. Every single problem in differential calculus uses this limit concept.
That's what enables it.
I'll start in limits, but I want to give you an overview like this, only with integral calculus. So I'm going to erase everything. And let's talk about, I may have to take a short break here. Public service is in the area. And they need to get in my backyard, so I might need to take a 3-minute break if they are out front. Let me just check before we go on. Hold on.
Yes, sir.
Oh, good. They're not to my backyard yet. I need to bury some cable in the backyard. All right. So this is integral calculus, which is all about finding the area under a curve. Same curve, x squared. This time I'll call it y equal x squared. Actually, I don't like that terminology. The f of x terminology works so much better from the get-go.
Yes, sir.
I like using it. And you'll see why.
Okay.
All right. So if I came up to you and you didn't know anything about calculus, how would you figure out the area under that curve? Any idea what you would do? This is what they did for thousands of years before Newton and Leibniz. They had real life problems where you had to figure out the area under a curve. Back to Greece, they had this problem. So what would you do if somebody gave you that problem?
Would you?
Let me give you a suggestion. Let's draw rectangles and fill up that area with rectangles.
Yes, sir.
Kind of get the idea here. This is hard to draw really well. You can see that it's an estimation.
Yes, sir.
And it's not going to be exact, but they didn't need it exact. Back in Greece times, all they needed was an approximation of the area under that curve. You can see that each rectangle goes a little bit to the left of the curve and a little bit to the right of the curve, or at least that's the way this one here, number 3, goes. So that should be a decent approximation for the area under that curve.
Yes, sir.
Now what we're going to do, what they did back in Grecian times, was start making those rectangles skinnier and skinnier and skinnier.
And skinnier.
So that I'm going to put an infinite number of them in there. And as I do that, in other words, as I let delta x approach 0, I end up with an infinite number of rectangles. And guess what else I end up with? The exact area under that curve, not an approximation anymore.
Okay.
Okay. So here's what we're going to do. We're going to call that well, you start out with sigma, which is the sum of the area of these rectangles.
Yes, sir.
As x goes, or delta x goes to 0. I could call that h again, but let's just use delta x dealing with integral calculus. Now, typically what you get taught is 3 months of differential calculus and then 3 months of integral calculus. Okay, so I'm only going to give you a basic overview, but this is it. This is how you figure out the area under a curve, is you split it up. And a better way than using rectangles would actually be if I use trapezoids.
Trapezoids.
Yeah, see that first trapezoid?
Okay.
Notice that it's a better approximation.
That's right.
Trapezoid goes like that. And it turns out that if you put a parabola on the top instead of a straight line, that's the best approximation yet.
So you can put a parabola on top of the...
Yeah, that's the math on that's a little bit harder. In fact, it's really hard. It's just that that's probably the best approximation technique. That's what a lot of calculators that do calculus use, approximation techniques. They don't use the method of calculus that gives you the exact answer. But some of these approximation techniques will be accurate out to like 5 decimal places. So accuracy maybe is important if you're trying to fly somebody to the moon. You wouldn't want an approximate thing.
Yes, sir.
But you'd want the exact answer. So there's various shapes you can put in here. I mean, there's rectangles, there's trapezoids, there's rectangles that have a parabolic shape at the top. But all of them lead to the same ultimate answer. It doesn't matter whether you use trapezoids or rectangles, as long as you use calculus and you let delta x approach 0. You will get the exact area under that curve, whether you're using rectangles or you're not really doing that anymore. Well, you are. The definition for integral calculus is beyond our level at this point. It's a little bit easier for differential calculus to understand. But the concept is exactly what I'm showing here. We're going to put as many rectangles as we can in there, and we're going to let the width of each one of them approach 0.
Okay, so it's another approaching 0
Yeah.
type concept.
And then another thing we can do is we can take this curve, rotate it about the x-axis such that we create an object like that.
Okay.
This is a solid object, kind of like a cone that you would wear on your head, a dunce cone.
Mm.
And we can figure out the volume of that object.
Huh.
How? By splitting that object up into a bunch of disks.
Oh,
Thickness of each disk approaches 0.
okay.
Okay. So, okay. I think I'm done with the overview here. Let's start talking about limits.
Yes, sir.
At least you won't need to ask yourself, why am I doing these problems? What is the limit of x plus 5 as x approaches 2?
Would that be 7?
Very simple.
Okay.
What is the limit of x over 2 as x approaches 0?
So that would be 0.
What is the limit of 2 over x as x approaches 0 from the right side, which is what that means?
X approaches 0 from the right side?
Mm-hmm.
Okay. So that would be undefined.
Correct. Actually, from the right side, you can say that that's infinity. We'll get to that in a second. Basically, I'm talking about this hyperbola.
Yes, sir.
And if I'm approaching from there, and I'm approaching 0 from the right, this thing goes all the way up to positive infinity.
Yes, sir.
If I'm approaching 0 from this side, it goes all the way down to negative infinity.
Ah, okay.
Okay. And one mathematical definition of a limit is it's got, for it to exist,
That's right.
it's got to approach the same limit from both sides. If you don't approach the same limit from either side, then that limit does not exist.
Okay.
So if I said, what's the limit of 1 or 2 over x, doesn't matter whether it's 1 over x or 2 over x, as x just approaches 0, that is undefined.
Oh, okay.
Okay, because from the left it's negative infinity, from the right it's positive infinity. They are not one and the same, therefore the whole thing is undefined.
Okay.
Okay, all right, let me keep going. So clearly, if the numerator goes to 0 or the denominator goes to 0, we can figure that out.
Yes, sir.
What's that limit?
X approaches 1. So that would be undefined?
Well, if you do direct substitution, you get 0 over 0.
That's right.
0 over 0 is not undefined, believe it or not. It's indeterminate, is what it's called.
Indeterminate.
Yeah, it's like infinity divided by infinity is indeterminate. It's not infinity and it's not 0. It can be a number. We'll get to that in a moment. So how do we come up with this limit here? Because we start off with 0 over 0. And all limit problems, by the way, the only hard ones are when it comes down to 0 over 0. If it comes down to a number over 0, you know it's undefined. If it comes down to 0 over a number, you know it's 0. So the only tough ones ever are 0 over 0 upon your first substitution.
Okay.
Okay? But we can do something with this. We can factor the top into x minus 1 times x plus 1. Bottom is still x minus 1. Cross
That's right.
2 out, and that whole function becomes x plus 1. Now, what is the limit of that as x?
2.
Yeah, exactly.
Huh.
So we started out with 0 over 0, but it turned into a number, 2.
Okay.
Okay?
Yes, sir.
What I'd like to do next is give you a bunch of limit problems. There are 3 main techniques. What this technique was factoring. That's a big one. That's going to solve most limit problems.
Okay. Factoring.
There's a couple of other techniques that you might not think about when you're trying to solve the problems. I'm just going to go to my textbook here and find some limit problems that we can do. Now you talk about hard. The epsilon delta definition of limits. It's another thing they do is some schools, in 10 years of tutoring calculus, I've only had one student. The very first session, she wanted to know if I could explain to her the delta epsilon definition of a limit, which was only developed 100 years ago, by the way. I mean,
Wow.
Yeah, Newton and Leibniz was 300 years ago, 350 years ago. But this formal mathematical definition of a limit is called the epsilon delta definition. And it might be the hardest thing in all of calculus to understand. And yet, there are some schools that they start right off with that. It's unbelievable. Even Saul Kahn, the famous Saul Kahn, says that that is way beyond what a Calc 101 course should be studying. Just no reason to study that hard of a concept that soon. You know, you learn calculus the same way you learn skiing. You start on the green slopes, the easy ones, and then you master them, and you go to the medium ones, and you master that, and then you go to the expert slopes.
That's right.
I think math should be taught the same way. You don't start off on the expert stuff. The stuff that just demoralizes people, confuses them, they don't understand it, they have no idea, and they just completely give up before they even get started.
That's right.
So I'm not going to do that to you. Okay, so let me put up some more limit problems and we'll let you work with them. Let's choose this color, it's a better color.
All right.
No, hold on. Yeah, I'll do it as long as I put it up there. It's not quite what I had in mind, but.
X approaches 1.
Mm-hmm.
So we would have to factor out the top. Or is that's not factorable?
No, first of all, always try substitution.
All right.
Remember, the only problem you're ever going to have is if after you substitute, you end up with 0 over 0.
Okay.
Well, you don't end up with that here. This is fairly straightforward.
So that's going to be 2.
Yeah, it is. All right. Yeah, I didn't mean to put that one up there here. I meant to put up something like this.
Okay. So that would be another 0 over 0.
Yeah, all of them are going to be that. I'm not going to give you any more that aren't 0 over 0. There's not much point in them. They're too simple. It's the 0 over 0 ones that present difficulties sometimes. Think factoring. That's the only thing you know at this point.
Okay, so x minus 1.
X cubed minus 1 is the difference of perfect cubes.
That's right. And that factored would be, and that factored would be x minus 1 times x squared plus x plus 1.
Very good.
And then you can factor out the x minus 1.
That's the key in all of these factoring problems. Once you factor it out, now resubstitute. What's that limit?
And you get 3.
Okay. You're pretty good at factoring, right?
Yes, sir.
Okay. It's one of the beauties of this is that I know you pretty good, and I'm not going to spend time doing stuff that you know how to do.
Yes, sir.
Just going to go forward. We might get done with calculus by the end of the summer.
Yes, sir.
At least to a point where you understand it.
Yes, sir. So as x approaches 0, that's another 0 over 0.
Right.
So would we have to square that? Or
Turns
not?
out not. There's a technique here where you're going to want to multiply the top by the conjugate. In other words, the top and the bottom. In other words, any fraction you can multiply by the number 1. Okay?
Okay.
Well, what my number 1 is going to be is the conjugate of the top, by the conjugate I mean that, over the same thing. That's the number 1.
That's right.
Right?
And that'll cancel out the radical.
Well, let's do it.
Well, on the numerator.
What do we get on the top?
So we would get x plus 1 minus 1, so we just get x.
Okay, we'll write it like that for a moment. And one thing you don't need to ever do is multiply this bottom. You just can always leave it like you find it.
Okay.
Okay, it's just the best way to do it. You wouldn't be able to multiply it anyway.
Yes, sir.
Okay. Simplify the top.
All right, so that's x, and we can factor out the x.
Resubstitute. I do have a 1 in that numerator.
So that the limit would be 1/2.
Bingo. Technique number 2. Let me see if I can find one other problem like this. Yeah, here. I'm still in the section where they're given easy ones. Here we go. Yeah. Yeah, let's do this one. Bet you can figure out what the bottom's going to be.
All right, the bottom will be 16, and the top will be...
Oh, no, hold on. The bottom will be x minus 16.
Oh, okay.
We know we're headed to 0 over 0, right?
That's right.
That's the essence of all of these limit problems.
So we would multiply by the conjugate of 4 plus square root of x. And so we would get 16 minus x for the numerator, and then x minus 16 quantity times 4 plus the square root of x as the denominator.
Okay, we want this limit as x goes to 16. Still 0 over 0, isn't it?
Yes.
Can I simplify anything?
Would you wouldn't multiply out the
Tell me what this is. A minus b divided by b minus a.
You could take out a -1.
That will do it. That's equal to -1 no matter what a and b are. So 16 minus x over x minus 16 can make this numerator read negative x minus 16.
That's right.
Now I can cancel out that with that, leaving a -1 in the top. Now resubstitute, what do you get?
Now you get 8.
-1 over 8.
-1 over 8. That's right.
That is the slope of that function when x is 16. If I were to graph that function on Wolfram alpha,
yes, sir,
and say, tell me what the slope of the tangent line is as x goes to 16, that tangent line slope is going to be -1/8. I won't take the trouble of proving that to you on Wolfram alpha, although that wouldn't be a bad exercise to show you how this works. In other words, remember what well, hold on a second. Let me rephrase that. Yeah, I'm not so sure about that. I might have to check at that. I'll bet I am. I'll bet that is correct, actually. But that's not really what we're talking about yet. Belay that differential calculus for a moment and try to function on, or try to conceive of these limits as just limits of functions as x goes to a certain value.
Okay.
Okay?
Yes, sir.
Remember this right there, because that is the only time you can cancel out things that aren't the same. Is if you have a minus b over b minus a. In other words, what we had there was we had 16 minus x over x minus 16.
Yes, sir.
And we can cancel that out and replace it with a -1.
Yes, sir.
All right. Good place to stop. We're not done with limits. We'll definitely still be doing limits next Tuesday. But I've shown you two techniques already. One is factoring, the other is multiplying by the conjugate when it's more complicated, and the third is all about trig. So that's kind of what we'll get into next Tuesday. to start talking about first derivatives of trig functions.
Yes, sir.
Okay? Garrison, I'll talk to you next Tuesday. Have a good rest of your week.
Yes, sir. You too.
Bye-bye.
Bye.